Is our last section in chapter 12.
Our test is on Monday.
If you would like it to be on Monday, Seth, we could arrange it. All right. So yesterday we developed this idea, this relationship between arc length and curvature, the arc length function, and how those two are related. How we've talked a little bit about the geometric properties of curves. I want to go talk a little bit more about that, and then we'll talk about acceleration. So if we said yesterday we have our curvature is K, and at some point P, and we said our radius, we wanted our radius of curvature to be inversely proportional, so we just said, okay, the radius of curvature is 1 over K. We call the circle with radius R that's tangent to the curve at point P. It's called the osculating circle. And we're going to say tangent to the curve on the concave side. So it makes sense that we're talking about the concave side because we're talking about the curvature, talking about the radius inside the circle, not the radius outside the circle. So on the concave side, we call that the osculating circle. Or the other way you hear it referred to is the circle of curvature. Osculum comes from the Latin and means to kiss. So it's a circle that kisses the curve. So we can think of the osculating circle as the circle, kind of the circle of best fit, or not the circle of best fit, but the circle approximation to the curve. So in Calculus 1, we talked a lot about the tangent line and how the tangent line at that point was an approximation to the curve if you're very close to the point. Well, the circle is tangent to the curve and it has the same curvature at that particular point. So it's the circle that is a good approximation to the curve. And I have a little demonstration visual thing that is that the one? There's the one I want. There we go. Osculating circles. So here we have a polynomial function. Here's our circle of curvature, tangent to the curve at a particular point. And then, where's my marker? And we can see as we travel along the curve how the curvature changes. As the curve flattens out, our curvature becomes smaller. As we're in a more curved part, the curvature gets larger, our circle of curvature gets smaller, radius gets smaller. At inflection points, it's going to change. And our osculating circle is always on the concave side of the curve. And then we have a nice trigonometric function. There's our osculating circle. So there's a very large curvature there, small circle of curvature, and then a very small, zero curvature there, it flattens out. And then at the inflection points on the other side of the curve. And then here's our logarithmic function. So it's very flat out here, not much curvature. And then the circle gets progressively smaller, 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 smaller. There. And then I have another demonstration. So that's our osculating circle. Circle of curvature, tangent at the point, and the same curvature at that particular point. I have another demonstration in 3D. Did I close that one? Is it this one? There we go. So here is a curve, a three-dimensional curve. So you're thinking of this, let me rotate it around. So that's looking at it from above, from the side. So here's our osculating circle of this curve in 3 dimensions. So it changes not only in radius, but its orientation changes. Let me put it so we can get a better view here. So the orientation of the circle of curvature changes as we go around this curve. So the curvature changes and the orientation. And that's related to, I mentioned yesterday at the end of the talk yesterday about the binormal vector. And the binormal vector is a cross product of the unit tangent and unit normal vector. And how it changes with respect to the arc length is a measure of how the curve twists. So this one is from the circular helix. So here's our osculating circle on the circular helix. The radius is constant, but the orientation changes as we move around the helix. And then here's an elliptical helix. So the radius is going to change and the orientation changes. So just kind of a visual picture of how the curvature changes, and this circle of curvature along this curve. Okay. I just like those. Those are nice pictures. So one thing that we are interested in doing sometimes is finding the center of that circle of curvature. So we want to talk, if we're using that oscillating circle as an approximation to the curve, that at that very close to that point the curve is approximately circular, with the osculating circle being the circle that represents it. So we want to find the center of that circle. So let's draw a picture and talk about how we're going to find we can find the equation of the osculating circle or the circle of curvature. So here are axes. Go the other way. And I'll draw the circle first because it's easier for me to draw the curve around the circle than the other way around. So here's our circle of curvature, and I'm going to draw our curve in blue. So we have some kind of curve like so. And we're going to say that this is the osculating circle. There's our point where it's tangent, and we want to find the equation of this circle. So we need to we know how to find the radius of curvature. We talked about that yesterday. We take the reciprocal of this, and we get the radius of curvature. But we want to be able to find the center of curvature. So let's draw a couple of more vectors. Here's a position vector to our point on the circle. So that is r of t. And we're going to draw a vector to the center of the circle of curvature. So we can find the components of this vector c. We'll call this vector c. So that's just a vector that points to the center of our circle. We can find the components of that vector. That gives us the coordinates of the center of the circle, and we can find our equation. Well, based on what we talked about yesterday, what vector is going to point, what vector that we're somewhat familiar with is going to point towards the center of the circle? The unit normal vector. So if the unit normal vector is pointing towards the center of the circle, how can I find the vector that goes from this point to the center of the circle? How long do we need that vector to be? The radius. So this vector is going to be the magnitude of our radius times our unit normal vector. The center of curvature is in the direction of the unit normal vector, and we know that r equals 1 over our curvature. So the vector to the center of our osculating circle, c, is our position vector of our point plus the radius at that point times the unit normal vector at that point. And this will give us the coordinates of the center of the circle. So if we're interested in finding the equation of the circle of curvature, this is probably the easiest process that we can use. So again, the osculating circle most closely approximates the curve at point P. Its tangent matches its curvature. The plane that contains T and N is called the osculating plane. So the I just want you to be familiar with these terms. You'll hear osculating circle or circle of curvature. The osculating plane is the plane given by T and N. The acceleration is always in the osculating plane. And then the binormal vector would be a normal vector to the osculating plane, the binormal vector, and we usually call that B is T cross N. And this is the binormal vector. And how that binormal vector changes as we move along the curve is called the torsion of the where we define the torsion by how the binormal vector changes as we move along the curve. So we use all of these things to analyze the geometry of curves in space. So questions about the osculating circle? Isn't that a nice word? All right. So let's go back to curvature and acceleration. I just wanted to talk about this a little bit of geometry, a little bit osculating circle, just a nice geometric idea. And now let's make the connection between curvature and acceleration a little stronger. So yesterday we said that our curvature, intuitively it should be related to the normal component of acceleration. The normal component of acceleration should tell us something about how the curve is curving. So let's look at our definition, or the way we expressed, not our definition, the way we expressed acceleration. We found that we could break down our acceleration into components, tangential components, and we said our normal components, and we came up with several expressions for our normal component. So a tangential component of acceleration and a normal component of acceleration. Well, here's our normal component of acceleration. Let's look at, oh, and I forgot one thing, this should be T prime. T prime, there we go. Let's look at T prime, because we talked about T prime in relation to the curvature. So the magnitude of T prime, we said was, or we know is the magnitude of dt. And we can write this in terms of our arc length parameter. So this is the rate of change of the unit tangent vector with respect to arc length times ds dt. We're using the chain rule there. Well, what was the magnitude of the rate of change of the unit tangent vector with respect to arc length? Anybody remember?
Curvature.
That's how we defined curvature. And ds dt, the rate of change of the arc length with respect to time was what quantity? Magnitude of r prime. That was our speed. And I can write that as our velocity. Let me make that a better V.
Wait, is that velocity?
Velocity, yes. R prime, or not velocity prime, velocity. So we can write, so T prime, magnitude of T prime, equals the magnitude of the velocity times the curvature. And we can say, we substitute this into this expression, and the acceleration is the rate of change of the velocity with respect to time times our unit tangent vector, our scalar acceleration, plus the magnitude of v squared times k times our unit normal vector. So we can write our acceleration in terms of our curvature. I could rewrite this because the curvature is the reciprocal of the radius of curvature. I can also write, and this should look familiar to, hopefully, to physics people, plus the magnitude of v squared over r times the unit normal vector. So when you talk about circular motion in physics, the acceleration is v squared over r. So this hopefully is for physics people, that's a familiar expression. So there's our connection, made our connection between curvature and the normal component of acceleration just a little more explicit. Questions there? Okay, sometimes you'll see acceleration expressed in terms of our arc length parameter. So I just want to write our expression for acceleration if we parameterize, or if we have a curve parameterized in terms of the arc length. So using the arc length parameter, and let me go back here really quickly. You'll see these expressions more in more kind of a science/engineering context, because the velocity and that's more what we talked about yesterday, is more of a dynamic property of the curve, thinking about something moving along the curve. When we talk about the arc length parameter, that you'll see that in more of a mathematical context when we're talking about when you're talking about more something that's the property of the curve, more of the geometry of the curve. So we know that ds dt, the rate of change of the arc length with respect to time, is the magnitude of our velocity. So we can write that the acceleration is the second derivative of the arc length with respect to time times our unit tangent vector plus the curvature times ds dt squared times our unit normal vector. So if we write our if we're expressing everything in terms of the arc length parameter, this would be the expression you would see for acceleration along the curve. And because we parameterized in terms of the arc length, what did I just do? Because I parameterized in terms of the arc length, this representation of the acceleration is independent of the parameterization. So just a couple of different ways of thinking about acceleration in terms of the curvature. And our normal component of acceleration has this relationship to the curvature. All right, questions there? Okay, let's take a look at a couple of examples to finish. So let's say we have y equals x minus 1 squared plus 3. We want to find point of maximum curvature. And the limit I'm going to write it this way, limit as x approaches infinity of our curvature. So intuitively, looking at this, what's this graph? If we graph this, what's it going to look like? Parabola. Where do we think the curvature is going to be maximum? At the vertex. Intuitively, the curvature should be maximum at the vertex, and our limit as x approaches infinity of the curvature of a parabola, what do we think the curvature is going to be? Think about the pictures that we saw, the osculating circle.
0.
The limit should be 0, right? Because the parabola is curved at the vertex and then it flattens out as x approaches infinity. So we'd expect the maximum curvature to be at the vertex and the limit to be 0. So let's look at that analytically. So we're going to use k equals, and this our expression for curvature in the plane. So this was what we came up with at the end of the day yesterday for curvature when we have y equals f of x. So we need y prime and y double prime. Not too bad. Y prime is 2 times x minus 1. Y double prime is 2. So substitute these in. So our curvature is 2 over 1 plus 4 times x minus 1 squared, and that is all to the 3/2. So what x value is going to make this a maximum? We could find the derivative of this and set it equal to 0, but we can do it an easier way here. X equals 1, because that makes the denominator, well, makes the denominator, well, this is 0. That's as small as that's ever going to be, right? So that makes our denominator the smallest. So at x equals 0, sorry, x equals 1. So at x equals 1, y equals 3, and we're at the vertex of our parabola, just like we expected. And the limit as x approaches infinity of our curvature is 0, just like we would expect intuitively. So we hope that when we define our curvature this way, when we work with our curvature, that it conforms to the way we expect things to work. And in this example, it looks like it does. All right, questions there? All right, let's look at another example. Let's just think about how this one's going to work. Y equals x minus 1 cubed plus 3. Where would we expect the curvature to be 0 here? So let's sketch a quick graph. Or not, I'm not even going to put axes on. What does the graph look like? Yeah, Ryan says. So it looks something like this. And where would we expect the curvature to be 0? At the inflection point, right? So, and for this particular curve, where would the inflection point be? 1, 3, just like our parabola. It's kind of like the parabola. And if we went through and did the same calculation that we just did, we'd find the curvature is 0 at that particular inflection point. That's curve swoop. That works. Either one. So questions about curvature? It's really all the only examples I wanted to do. The rest, finding the curvature, just involves using our formula, finding our prime, our double prime, all of that kind of thing. I just wanted to do these couple of examples just to show that the curvature kind of conforms to our intuition about how it should work. If you look at the curvature of something moving in uniform circular motion, you'll find that the curvature, when you find the radius of curvature, it gives you the radius of the circle in which you're moving. I think you might have a homework problem or two that have something to do with uniform circular motion. So just to kind of confirm that what we came up with for curvature actually makes sense in terms of how we think about it. All right. I brought some to do something a little different.